Hello, good evening. Today is Friday, March 26th, 2021, and I'm continuing with my video presentations. As I have mentioned, since we started working from home for COVID-19, during COVID-19, I have been giving a series of video presentations. Most of them are based on the keynote addresses that I have given over the past year. And so what I do is record the presentation and send the video link to the organizers. So these are the backup presentations. And I'm also present during the keynote live presentation. So I give the live presentation as well. Some of the talks are also some historical talks, meaning topics like access control for database systems, and so data mining for malware detection. And today's talk is going to be on data privacy. So I've been giving variations of this talk over the past probably around 10 years, starting probably 10 years ago. And then over the years, I've been sort of modifying this presentation. And so this is, I would call more or less a historical presentation. So again, it's on data privacy. Oh, by the way, I'm Bhavani Thuraisingam from the University of Texas at Dallas. Okay, so what I'm going to do now is share my screen. Okay, why is this? Okay. Great. Okay, great. So the talk is data privacy. And so I'm going to talk about what is data privacy and then go on to discuss various aspects of data privacy, including privacy preserving data mining, platform for privacy preferences, as well as data mining for privacy and some of the data mining privacy problems that can result due to data mining, and also talk about policy processing for privacy control. Okay, so what's privacy? So different communities have different definitions, right? So for the medical community, privacy is about a patient determining what patient medical information the doctor should release about him or her. Financial community, a bank customer can determine what financial information the bank should release about him or her. In the government community, I believe FBI would collect information about US citizens. However, FBI determines what information about a US citizen it can release to, say, CIA. So it's a little bit different aspect of privacy. So what are some of the privacy concerns? So for the medical and healthcare, employers, marketers, and others knowing of private medical concerns. So because if marketers can know your private medical concerns, then they can sort of bombard you with the messages, right? Because they know the sensitive information. Financial area, access to sensitive personal financial information. For security, you allow the access to the individual's travel and spending data, and allow access to web surfing behavior, because I can stay in my own home and surf the web, but it's not the other person, it's not the business of other people, right? What I do, of course, if I do some criminal activities like search for, say, child pornography or something, that's a different matter than the law enforcement. It's a law enforcement matter. But in general, whatever I do, my web searching behavior, it's not, it's my private behavior, right? So, and also similarly, allowing access to individuals' travel and spending data. So in the marketing, sales, and finance, allowing access to individuals' purchases. And there's also other aspects, right? Access to sensitive data, such as social security numbers and so on. Okay, so is data mining, we've heard about data mining, and I've given talks on data mining. In fact, in one of the earlier presentations, I talked about data mining for malware detection. So data mining as a threat to privacy, right? So what is it about? Data mining gives us facts that are not obvious to human analysts of the data because you can dig and extract information. Can general trends across individuals be determined without revealing information about individuals, right? So for instance, you don't want to say that John Smith has cancer, but you might want to say that in a particular area of Dallas-Fort Worth, that's where I live, certain people have, there is a prevalent for people to get cancer. So there are different types of threats, right? So one is to combine collections of data and infer information that is classified or private. That is typically the inference problem. Also, we call it the privacy problem. So disease information from prescription data. And apparently during Desert Storm, I don't know whether this was true or not, there's military action from pizza delivery to the Pentagon. Then you know that something is going to happen. So in some cases, you need to protect the associations and correlations between the data, and these correlations are sensitive. And that's also in a way that came from the definition of the inference problem. But privacy is even more than that. With respect to privacy, in many cases, we may need to protect the individual values, like the person's disease, and not the results from, say, data mining. The area where she lives has a higher incidence of lung cancer. Okay, so that has to be known for epidemiological studies. Okay, so some data privacy basics, how to share data without violating privacy. So for that, we need to talk about what is privacy, right? Disclosing the identity, right? My identity, and disclosing the sensitive attributes. And those sensitive attributes, my financial data, my social security, my web surfing patterns, as well as my healthcare information. So current techniques for structured data. So you have to talk about measures of privacy, right? So the various definitions have been developed. K anonymity, L over the last 20 years. K anonymity, L diversity, differential privacy, and secure multi-party computation. And I'm going to talk about two of these, K anonymity and secure multi-party computation. So I have a more advanced lecture on data privacy that I give to my students. And there I talk also about L diversity, differential privacy, as well as T closeness. So there are various other definitions. So what is the problem? Publishing private data while at the same time protecting individual privacy. Challenges, how to quantify privacy protection. So you need sort of metrics, and how do you quantify? How to maximize the usefulness of published data, and how to minimize the risk of disclosure. Because what is the point in randomizing, perturbing, changing all of the data so that at the end, it all becomes really useless, because the data could be, because you have masked it so much that it cannot be used. Right? It's not of much value. So there's always a trade-off between the cost for enforcing all this, randomization, perturbation, masking, and also the utility of the data. And what's the risk of disclosure? Because you don't want the private data to get into the wrong hands. Okay, so sanitization and anonymization, automated de-identification of private data with certain privacy guarantees, as opposed to, say, HIPAA, Health Information Portability Act, formal determination by statisticians. That's a requirement of HIPAA. There are two major directions, perturbation and anonymization. There's also actually randomization, including random values, but most often it's perturbing. Again, that's adding random noise or slightly modifying the data. So it's really, we are looking at it both perturbing and randomization, more or less in the same way. Anonymization. So I'm going to talk about K-anonymization. So you want to anonymize data, right? So to anonymize data, removing the unique identifiers is not sufficient, right? So just removing the social security number, because what you really want to do is make it as difficult as possible for the adversary to infer the private information. So you may want to, sort of perturb the data a little bit, or anonymize the data so that there are multiple records, with similar trends, so that you don't identify that John Smith has cancer. It could be John Smith or Paul Richard, or Mary Williams. So one of the three could have cancer, right? So you don't know which one. And if you add a fourth person, you are adding even more doubt, right? So quasi-identifiers, maximal set of attributes that could help identify individuals, right? So assumed to be publicly available, like voter registration lists. As a process, remove all unique identifiers. Identify quasi-identifier attributes and model adversaries' background knowledge. Enforce some privacy definition like k-anonymity. And so I'm going to come to that. So one of the professors at Harvard, Professor Latanya Sweeney, she is like the expert on data privacy, extremely well-known professional and a professor, PhD from MIT. So this is her work, re-identifying anonymous data. She was the first to come up with sort of a measure for privacy. In fact, she came up with k-anonymity. So she said 37 US states mandate collection of information. She purchased the voter registration list for Cambridge, Massachusetts. At that time, 54,805 people. And you have ethnicity, there are various properties, like medical data, ethnicity, visit, diagnosis, procedure, medication, and total charge. And voter list, name, address, date registered, party affiliation, date last voted. And then the intersection is zip, birth date, and your gender, right? That's the intersection. Both sets of data, right? They have something in common. So 69% unique on postal code and birth date. So 69%. 87% US-wide with all three. Okay. So solution, she's saying k-anonymity. What is k-anonymity? Any combination of values appears at least k times, right? So you have any combination of values. If it's two anonymity, at least two values, right, belonging to two different people, right? So those rows appear at least twice. 3 anonymity appears 3 times. So she developed systems that guarantee k-anonymity, minimize distortion of results. So the higher the k, the more doubt that you are creating. And so k-anonymity, each released record should be indistinguishable from at least k minus 1 others on its quasi-identifier attributes. So each case, so if you have 3 anonymity, right, every record, there must be at least 2 others because there are 3 records with the same values. Alternatively, you can say cardinality of any query result on released data should be at least k. But we look at more the first definition. K-anonymity, the first one of many privacy definitions in this line of work. L diversity, T closeness, invariance, delta presence, and differential privacy. Complementary release attack. Different releases can be linked together to compromise k-anonymity, right? That's the problem, because maybe you can prevent it in one data set, but if you have multiple data sets, right, and you can link together, and k-anonymity vanishes. Solution, consider all of the release tables before releasing the new one and try to avoid the linking. This is sort of very similar to some of the early work we did on inference. By the way, my next presentation, which is going to be a week from today, April 2nd, and that's going to be my complete work on inference, right? Just like Professor Sweeney, right? She is the person for data privacy. I, in a way, made my name. You know, I got these awards like IEEE and ACM fellows and my, you know, IEEE and ACM awards and so on. Really, a lot of it started with my research on the inference problem. Anyway, coming back to this, consider all of the release tables before releasing the new one and try to avoid linking. Other data holders may release some data that can be used in this kind of attack. Generally, this kind of attack is hard to be prohibited completely. Okay, so that's k-anonymity. Now, we get to some privacy problems and some potential solutions. Remember, inference problem, the way we define, it's the process of forming conclusions from premises. If these conclusions are unauthorized, so you get legitimate premises and you get unauthorized conclusions, then there is a problem. Inference is the process of deducing sensitive information from the legitimate responses received from user queries. Potential solution, we call it privacy constraint or / privacy policies. In those days, we called it privacy, security constraints, or later privacy constraints. But today, the word that we use is policy. Actually, I'm doing a certificate in public policy analysis. It's ongoing from the London School of Economics, which I finish probably in about a month. And so that certificate, it's about public policy. But then when we look at the policies, it's more general statement. When we talk about these constraints, or when we call it policies, these are very specific statements. So I have a feeling now, after studying a little bit about public policy, I believe that we are using the word policies in the cybersecurity sense a little bit incorrectly. Policy is sort of very high-level statements that you set forward, right? So anyway, I'm going to look at that, maybe think more about it when I'm doing my assignments for my course. So anyway, so second is privacy violations that result due to data mining. As I said, you can mine and extract those nuggets, right? And those nuggets could be highly private, or the individual, privacy preserving data mining is that their individual data values could be private, but then you want to do data mining to get information like people who live in this part of the country, have a higher incidence of, diabetes or COVID-19 or cancer or whatever. That's number 2. 3, privacy violations due to unencrypted data. Of course, if you don't encrypt the data, you can get all the sensitive information. Potential encryption at different levels. Some areas, some parts, you may have very strong encryption. There's also attribute-based encryption. So many developments since I first, presented this work. And so I first presented this work actually probably about 20 years ago. Some charts, this particular chart. Privacy violation due to poor system design. Potential solutions, of course, you've got to apply good software engineering, privacy engineering, security engineering. Develop methodologies for designing privacy-enhanced systems. Okay, so what is privacy constraint? I'm also calling it policy because that's what the security folks have been calling, although now I want to think twice before using the word policy. But for now, let's call it either constraints or policies or rules. Privacy constraint processing, based on prior research in security constraint processing, such as you have a simple constraint, an attribute of a document is private if it pertains to healthcare records. If it pertains to, say, my hobbies, that may not be private. Content-based constraint, if document contains information about my health records, then it's private. Association, 2 or more documents taken together, it's private, but individually, it could be public. Release constraint. So after you release the, say, last 4 digits of your social, you don't want to release the first 3 because then you only have 2 numbers, the middle 2, right? And so how many combinations can you have for those middle 2 numbers? So the whole idea here, our solution is to augment a database system with a privacy controller for constraint or policy processing. So we took our work for inference. And as I said, next Friday, I will have my complete the 60 charts, I believe, on my work on the inference problem. So you have the user interface, you have the policy manager, or I call it constraint manager, you have the privacy constraints, then you have a complete design, right? Some of the data schemas are handled during database design. So you want to design the database, you have public segments and private segments and semi-private segments. So maybe you design the database so that the data goes into the appropriate segments. Then you want to do as much processing as possible during updates. So you take all the policies or constraints and compute the privacy level of the data. So the data could be highly private, semi-private, moderately private, public, and so on, right? And so that you compute the level and then enter the data into these appropriate schemas, right? The metadata. Then much of the work is handled during the, you want to do as much work as possible during updates and database design so that you want to minimize the work during queries, because we are assuming that you are posing many, many queries. 95% of the time it's for query, only 5% of the time it's update, and the schemas are not changing. Under those conditions, this design works very well because query operation is the most expensive operation, right? Because lots of policies, not just expensive actually, because it's also time consuming, got to give the answers because we don't have the time to wait for 1 hour for the answer. We want the answers, especially these days, very quickly. So many policies are processed during queries. And so you take the results and then you also check to see what results have been released prior, have the last 4 digits of the social security number released, then you don't release the first 3, right? So that's the architecture for policy processing. So some people have criticized. So I have, we have designed and developed a similar architecture for inference, and we obtained patents, and it was, lots of interesting work that we have done. But some people criticized and said, you don't, because remember, this work initially for the inference, we did it in early 1990s. And so at that time, who would have thought that storage would be so cheap and we have fast processors, we have the cloud? We didn't. So people said that, oh, it's going to take ever so long and you need to trust the entire system. My goal was to come up with those interesting techniques so that you can apply for multi-level security, you can apply for discretionary security, you can apply for privacy, you can apply for any type of system, right? Nevertheless, some people said that you want to do your design, especially we are assuming that the data is not changing. So that is changing often. If that's the case, you want to design your application and then see whether there are any privacy violations. So for instance, a dark line and boxes are private information. So for instance, patient John, we know that he has an address, but we don't want to give out the address, okay? And he's traveling frequently to England. Or you can say, see, this is sort of a semi-dark line. So you don't want to tell everyone that he's traveling, but you know that there's a country called England. But now what disease does he have? Because many people, especially the culture where I used to come from, you don't want to tell people that you have cancer. Maybe things have changed now, but you want to sort of keep it hush-hush. I don't know why. Because cancer, so what is wrong in cancer, right? I can understand those days people keeping quiet if you have a mental illness. Although today, there's nothing wrong because the way I look at it now, mental illness for me right now is a physical illness. It's just like you have a sort of an enzyme problem in your heart, and then that could cause you chest pains, right? You can have maybe some kind of a hormonal imbalance or maybe I'm not a medical doctor, by the way, some enzyme imbalance or something. So that is why the brain doesn't function as well as it's supposed to, just like the heart or just like the lung. So I don't see any reason why people should feel embarrassed about mental health. But then, of course, people do. But at least at that time, as I said, 40 years ago, right? People were more concerned about mental health, but I was surprised because people didn't even want to talk that they had cancer. But in any case, at the private level, John has got cancer. But at the public level, they tell everyone, oh, he's having the flu or influenza, right? So the whole idea is to design this application using some semantic model or some knowledge representation scheme and reason using the reasoning engines developed for those knowledge representation schemes like semantic nets or conceptual graphs, and more recently these knowledge graphs, and reason and say, okay, this design is wrong. So you may want to, your classification is wrong. So to try and find out problems before you design your database and your, and your policies and your query processing and the update processing. So before you do all this in this picture, you want to design your application. Okay, so that's the privacy policy processing. Now, data mining, privacy preserving data mining, right? So what are we doing here? So I believe that I was the first to introduce the idea, among the first, the privacy violations that could occur due to data mining, yet you need to apply data mining for security, like cybersecurity and national security. So I gave this present keynote address at the IFI Database Security Conference in Como, Italy. And then at the Pacific Asia Data Mining Conference in 1988, and that was in Melbourne, Australia, and subsequently published, I call it a landmark paper because when you are a program director at the National Science Foundation, That was in 2002 when you published a paper, because you are the one who is giving out money. So when you publish a paper at the CKDD magazine, then of course everyone pays attention and that paper gets a lot of references. So that's why I sort of brag a little bit and call it a landmark paper. Okay, no one else has called it a landmark paper. So anyway, so that spawned a whole new area of research. Privacy preserving data mining. The early people to do this work was Rakesh Agrawal and his team at IBM Almaden Research Center. However, we at MITRE Corporation, I was at the time with MITRE Corporation, and my colleague, Dr. Chris Clifton, he did some breakthrough work on this early work on data privacy and inference and data privacy. So some very interesting work. But in any case, the IBM guys, what they did was that you have the original data, you add noise, so you have the noise added, slightly modified, you have the modified data mining process, and the final results. But the final results should be more or less the same. If you cannot figure out that the people living in certain parts of DFW, higher incidence of, say, cancer or COVID or whatever, then what's the point in doing data mining, right? So the end result should be same, even though you have modified the original data. Instead of saying you are 25 years old, you say maybe you are 26 years old. So it doesn't really make that much of a, hopefully it won't make that much of a difference. So then when I joined the university after MITRE and NSF, when I joined the university, my first student, Dr. Lee Liu, and we also, one of my colleagues, Dr. Murad Kantorjalu, by the way, he happens to be Dr. Chris Clifton's, one of his early PhD students at Purdue University. But anyway, so Chris and I, we were at MITRE, then I went to NSF, and then Chris went to Purdue, and then Chris's student then joined us. Right, and that was between 2005 and 2008, privacy preserving decision trees and the perturbation method. Okay, so so at that time there came privacy preserving association rules, privacy preserving decision trees, privacy preserving this, that, and today we have privacy preserving machine learning, privacy preserving deep neural networks or deep learning. So anyway, so that was in the, probably around 12, 13 years ago. But then in 2014, right, by now we have got big data, right? It's not just data mining, security, and privacy. So in 1993, we did work on what we call massive data. At that time, we said, we know how to do terabytes, but we don't know how to manage petabyte size data. So, but that was then. And then 20 years later, in 2014, we've got this massive amounts of data. We have got all these technologies. We've got the cloud, we've got the edge, we've got all this high performance computing. And so then came big data, 5 V's, volume. I always keep mixing this up. Okay, let me try and get it right. Volume, velocity, so volume is the number, the amount of data. Velocity is speed in which you have to access the data. Volume, velocity, variety, the heterogeneous data. Veracity, the accuracy of the data. Value is the utility of the data. That is big data, right? So, okay, so then there is now big data. Imagine privacy could be exacerbated, right? Even the inference problem could be exacerbated. So we hosted an NSF workshop on this topic in September 2014, and Dr. Chris Clifton asked me to present these results because he was at NSF at the time, at the Interagency Working Group, all of these agencies in Washington, and that was in February 2015. And that spawned many research topics in data privacy, research projects, including like the DARPA projects and NSF projects and so on. Okay, so now, so I'm continuing with privacy preserving data mining, so motivation. Now, what has happened in privacy preserving? So this is really my take, okay? So when Chris and I worked together, 1995 to 2000, we said we want to give cover stories to prevent people from useful results, to infer useful results from minings. So we said we can introduce cover stories to give false results, or only make samples of the data available to various groups so adversaries are unable to come up with the useful rules and predictive functions. So I presented this at a data conference. I don't think it was PAKDD, I think some other conference. And it was a data conference. Oh, I was really, people got so upset with me. How can you even talk? These were data mining researchers. How can you even talk about giving cover stories and bad results, so that, and false results. I mean, then if you give bad results, because right, it's like garbage in, garbage out. If you give bad results, then you can have the best data mining tools, but your results are going to be all, of absolutely no value. So they are saying, essentially it's like you are setting us up to fail at the beginning. So that was abandoned. Then came the randomization, perturbation, anonymization. That was from the IBM work, introducing random values or perturbed data into the data and or results. Challenge is to introduce random values without significantly affecting the data mining results. So give a range of values of results instead of exact values. And this sort of research, is privacy preserving data mining is still continuing, right? So as I said, we are now coming up with privacy preserving deep learning. Then you have secure multi-party computation. Each party knows its inputs, right? So we are in a room, each one of us has a secret. So we want to take all our secrets and mine and come up with some useful results about the illnesses that we might have, general. So I may have cancer, I encrypt it and put it in a basket. And my colleague may have COVID, and so she puts something in the basket. My other colleague could have AIDS, and so he encrypts it, puts it in the basket. So all of us encrypt our secrets. And then our data mining tool works with these encrypted data, right, the secrets, and then comes up with the final result, which says that the people in this room, right, there is a predisposition for the folks in this room to have, let's say, lung cancer. Okay, but we don't know who has lung cancer yet, because assuming that we are not coughing and we are not doing anything. Okay, so that is what we want to find out, right? The individual values, individual secrets we are keeping. So each party knows its own inputs, encryption techniques used to compute the final results. That's privacy preserving data mining, some history. So I will say these are rough dates, right? This I would say sometime around 2005 to now. Okay, so right, so cryptographic approaches, as I said, I got this from Professor Murat Kantarjalu, right? Some of these charts, this particular one, secure multi-party computation. So he's one of the experts on this topic. It uses distributed data mining because there's a group of people, right? So it's distributed, not just singles, each of us having a secret. Provably secure under some assumptions, learned models are accurate. Efficient specific cryptographic solutions for many distributed data mining problems are developed. And it also works sort of in a distributed heterogeneous database environment. You mine each database and put it all together and then come up with a combined result. So there's also malicious model is also explored recently. So the workshop, I don't know which workshop, I think it's the ICDM, International Conference on Data Mining Workshop, or whether it was the KDD. Yeah, it was the data mining workshop in 2007. And that was held in, I think, Omaha, Nebraska. So we assume that the parties are semi-honest. That means they are not going to lie or give false stories. But many secure multi-party computation-based privacy-preserving algorithms share some common sub-protocols like dot products, summations, and so on. So the whole idea, and so what Dr. Murat has done is very interesting. He's also applied game theory, because what happens if the adversary is not entirely, if your model is not entirely honest, right? A malicious model. So there's a lot of development since then. And I've talked about it in some of my keynote addresses on adversarial machine learning. So I'm not going to talk about it in this presentation. Okay, so again, continuing with the cryptographic approaches, what are the drawbacks? Still not efficient enough for large data sets, right? Petabyte size data, or maybe now we have gone beyond peta, we have gone to zeta and maybe even exabytes. And we are assuming the model is sort of semi-honest, but that may not be realistic. The real world, you have malicious models, so the computations could be even slower. And some new directions, new models that can trade off better between efficiency and security. So we look at things like efficiency, security, risk, and utility, and a lot of work on applying game theory, incentive issues in privacy preserving data mining. And then you want to combine anonymization and cryptographic techniques, right? That's also a lot of work in this area. Okay, so this is my student, Li Liu. Remember, she did some very interesting work on perturbation. So she says distort the data while still preserving some properties for data mining purposes. So she talked about to what extent should you distort the data, right? So she says the data owner will apply the perturbation techniques, right? And then you have apply adapted data mining models. Sorry, not here, you go here. And so it's the data is perturbed, and then you have the attackers trying to attack, right? So you have the perturbed data, but still it could have, maybe even more malicious, whatever. And so these are the data mining researchers, and they are applying some of the adapted data mining tools. And then these are the patterns, right? So this is sort of a kind of a repeated process. So some of these perturbation techniques could be additive based, multiplicative based, condensation, decomposition, data swapping. So a number of perturbation techniques. So she's done some very good work, Dr. Li Liu. And after a PhD, she worked for eBay as a scientist, research scientist. And now she's a big project manager at a big, I believe it's a big retail pharmaceutical sort of company. Okay, so perturbation-based approaches for privacy-preserving data mining. And the goal is to achieve, so this is something she said, it's very interesting she did work, achieve a high data mining accuracy with maximum privacy protection. So she says at the one end, on the one hand, you are absolutely concerned about privacy. So do not give out any information. So 100% privacy. At the other end, right, you don't care about privacy, but you are so obsessed about the data mining results, right? That's the other end. So you want to be somewhere in between where that's their desirable goal, right? So that's where we want to be, sort of a trade-off between the two. And then she says privacy is a personal choice. So should enable individual, should be adaptable for individual preferences, right? So privacy level, top privacy, high privacy, medium, low, supply user with different levels. And so I say, look, I want this level of privacy. It's fine for me for high level of privacy, right? So then what you do is it's like plugging and playing, plug and play. Match with different perturbation interval lengths, that's the interval lengths, hence different perturbation levels and with respect to different privacy levels. So top privacy, it's this much perturbation, high privacy. And so top is, so the thing is you have A less than B less than C. L is a standard interval length, okay? So when you have top, this is what you get. High, that's the interval length, medium, and then the low. So you do this depending on what the privacy level that the user has specified. And she did a nice implementation on this and published it at ICDM 2006, I believe. It might have been a workshop. Okay. So perturbation-based approaches for privacy-preserving data mining. The trend is to make PPDM approaches fit in with realities, right? So we investigated perturbation-based approaches with real-world data sets, and we give applicability study to the current approaches. We found out the reconstruction of the original distribution may not work well with real-world data sets. Sometimes we found that reconstruction, because we have to reconstruct the data, right? The distribution. Distribution is really a hard problem. Should not use as a media step, probably as a first step, right? Initial step. Try to modify perturbation techniques and adapt some data mining tools. And that's what, so we have looked at decision trees and various other types of data mining techniques. Okay, so then the whole idea is person specifies what level of privacy he or she wants, and then we come up with tools. That's the whole idea. Okay, so now I finished privacy preserving. These are the two things I wanted to talk about. I just want to talk about confidentiality, privacy, and trust, because we hear these words so often, right? So this is what we really mean. Before I, as a user of organization A, before I send the data about me to organization B, like my social security number or my purchases or my credit card, I read the privacy policies enforced by organization B. If I agree to the privacy policies of organization B, then I will send data about me to B. If I do not agree, then I can negotiate with organization B. So that's the privacy aspect. Now, even if the website states that it will not share private information, do I trust the website? That's another question. That's where trust comes in, right? It says, here are my policies. But do I trust the website to enforce those policies? And then the confidentiality is the opposite, right? Confidentiality is enforced by the organization. Privacy is determined by the user. Therefore, for confidentiality, the organization will decide, or the website or the web server, whatever, a database server will determine whether a user can have the data. So when I'm querying, the server will say, okay, look at all the security policies and decide, can I give this user information to this so-and-so, right? That's confidentiality. Privacy, I determine what my privacy, what level of privacy, and confidentiality, in a way, the organization determines what information. But in both cases, either myself or the organization, do we trust? Does the organization trust me to give me this top secret data, right? So that's the whole idea. So we wrote a very nice paper about, I don't know, this was over a decade ago, on bringing in confidentiality, integrating privacy, confidentiality, privacy, and trust into a system. Okay, so then how do you specify all these privacy preferences, right? Like we said, the system will specify, okay, when I want to enter some information into the website will tell me, here are my privacy policies. So what are these privacy policies, right? How can you express these privacy policies? So remember, every time we go to a website, these are our privacy policies. Do you agree? And then we check. But how do you specify that, right? So what language? So P3P is an emerging industry standard that enables websites to express their privacy practices in a standard format. The format of the policies can be automatically retrieved and understood by the agents. It was the product of the World Wide Web consortium. That's Sir Tim Berners-Lee's consortium, because he's the father of the web. He created the World Wide Web and the consortium, and then he came up with ways to specify, the consortium came up with ways to specify the platform for privacy preferences. So when a user enters a website, the privacy policies of the website is conveyed to the user. If the privacy policies are different from user preferences, then the user is notified. User can then decide how to proceed. Several major corporations were working on P3P, like Microsoft, IBM, HP, NEC, Nokia, NCR, and so on. Websites have implemented P3P. Semantic Web Group has adopted P3P. P3P initially used RDF, so when the semantic web community came up with the platform for privacy preferences, they first used the RDF, resource description framework, to specify the privacy policies, right? P3P policies use XML with namespaces, but more recently, XML has been used for almost everything. So these days, the websites are using XML, although the initial standard was based on P3P. So P3P has its own statements and data types expressed in XML. P3P schemas utilize XML schemas. And P3P was released in not actually 20,005, it's 2005, right? For 20,000, we need to wait for 19 more centuries, I believe. No, more than that. To come to 20005, I think we need to go 19 millenniums, I think. Anyway, so here's a catalog shopping example. What's this whole purpose in P3P? Your name will not be given to a third party, but your purchases will be given to a third party. And that's the way, there's various ways to specify. I'm not giving the details, but it sort of gives you a flavor how these websites are implementing their privacy policies at the meta level. Okay, so P3P and legal issues. P3P does not replace laws, right? P3P, it works together with a law. What happens if the websites do not honor their P3P policies, right? So it's policy versus law, right? Then appropriate legal actions will have to be taken. XML is a technology to specify P3P policies. Policy experts will have to specify the policies. Technologists will have to develop the specifications. Legal experts will have to take actions if the policies are violated. So, of course, when the policies are violated, then of course we've got to bring in the lawyers. Okay. This is something that I do a lot. I've done a lot of work on information sharing between organizations with respect to security. So all I'm saying is you can do this something very similar with respect to privacy. So organizations sharing data according to privacy policies, right? So you have organization A, you have a set of data and policies, B has data and policies, C has data and policies. So you have a federation. These three form a federation, Federation of the United States or the European Union Federation. So so you are more lenient to your local folks, right? So you have less policies for local. So if you have, say, France, Germany, and Italy. So the France, for the French people, right, accessing the data, you give it out more freely, but you have export data and policies for Germany and Italy. So I would have said, France, Germany, and UK, but UK is out of the European Union now, right? So France, Germany, and Italy. So you export the data and policies, what data can be shared, what are the policies, and then whenever you query for the federation level, you have to look at what the policies are and then decide what information to share. So these could be security policies, these could be privacy policies. Now, if you look at one of the earlier presentations on cloud-centric assured information sharing, I actually talk about our actual design and implementation of the system. Another thing that I wanted to talk about, we sort of abandoned this, privacy preserving surveillance. So I had 3 students, right? One student developed a face detection and de-recognizing system. Another student developed suspicious event detection. When you're crouched up or when you walk in a certain way, is the person's behavior suspicious, right? So we have all of this video data, comprehensive security report listing suspicious events and people. So you have some manual inspection, some suspicious event detection, but then we wanted to bring privacy into this. So what we are saying,